Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture entitled Newton. At the end of the beginning lecture of Newton's method, we posed this problem and you were working on this, and you may have solved this, but if not, I'll give you another chance. You know what to do. Let's see how you did. Now, first of all, I told you to use your initial guess to be 1, and certainly we know at 0 this is negative, and at 2 this is positive, so we're guessing the midpoint of the interval, which is something you can do if you don't have any other insights to do, because you know there is a root in there somewhere, and that will get you started. And again, what we're doing is we're using this 1 in our first step, and then we're going to be computing this, looking at the tangent line and calculating what that point is. So here's what happens. So first of all, we have to find the recursion formula. So f of x is x squared minus 2. So f of xn is going to be xn squared minus 2. And f prime of x is 2x. So f prime evaluated at xn is going to be 2xn. And so the n plus first step is going to be the previous value minus this, and you can simplify that to be this expression. Now, even though there's a lot of calculation making this maybe not a good exam problem, this is a good exam problem asking you to compute this. So let's do some 3 iterations. So this is the line where n equal 1, because I told you to start with n equal 1. So we take 1 and we plug 1 into this equation, and I get minus 1. And then I plug 1 into this equation, and I get 2. Then I look at the ratio, and that is going to be minus 1/2. And then what I'm going to do is I'm going to subtract that from my value of xn. And so when I do that, what will happen is that for xn minus f of xn over f prime of xn, for xn being 1, I will get this. And one of the things that is not shown in this table, but it's not a bad idea, is to keep monitoring this difference, and this is going to tell you when you can stop. So now this value here is the one that we called x2. And so now we're going to do all of those substitutions again, and this is x3. I put it down here. I go through and do this calculation. This is x4. Now I said 3 iterations, so we've done 3 iterations, and we're within this much of the exact root. It's actually pretty impressive, isn't it? Here's another problem for you. Use Newton's method to approximate the zeros of this cubic polynomial. And here's kind of a graph, but you can see that if you take minus 1, it's going to be positive. If you take minus 2, it's negative. And I'm just going to suggest that you take, and this, I alternate between using zeros and ones, but this is your first step. It is going to be minus 1.2, which is somewhere near the root. And again, note we're using the intermediate value property for continuous functions to help us figure out what might be an appropriate guess. You know what to do. Let's see how you did. So xn plus 1 is equal to xn minus f of xn over f prime of xn, and that's going to equal this. This is what the function is evaluated at xn, and when we take the derivative of that, that's going to be 6x squared plus 2x, and it is minus 1, so this is what we get. So we're just going to be plugging things in. So when we start, this was our initial value. We plug them in, we do the calculation, we get this is 2. We plug this one in, and this is what I get for it, 3. Plug all these in, this is what I get for 4. And I could be monitoring how close. But if you look here, you can see that, oh, this, actually, this, Actually, here we start having the round off happening the same. So this number is the same as that number, is the same as that number. Now really there's additional decimal points that are happening here, but we didn't care about that because we only wanted them to go out to the, let's see, that's tenths, hundredths, thousandths, 10,000ths place. And you see these things are locked in as we went from there. So we could have even stopped earlier. Okay, let's do another example. I want you to consider f of x equal the cube root of x, and use Newton's method to find the approximate zero of the function for x1 equal, and that's your initial value, is equal to 0.1. You know what to do. Let's see how you did. Well, what happened here is you crashed and burned. Now you take the derivative, and the derivative of x to the 1/3 is 1/3 x to the minus 2/3. So you can substitute that in, and you can simplify this expression. You should check this, but you get x in minus 3x in because of the things that calculation that we do there. And so x in minus 3x in is minus 2x in. Then we start going through my table. But look what happens with the values. We get, our first guess was 0.1, then we go to 0.2, then we go to 0.4, then we go to minus 0.8. This is out of control. It is not converging. It continues to increase in absolute value of the magnitude as n goes to infinity. This limit does not exist. Now, the reason this fails is because the derivative fails to exist at the actual root. You see, the real solution to this of f of x is equal to 0 is x to be 0, and the derivative has x in the denominator, so the derivative is not going to exist, and that's why this fails. Now, in practice, what engineers will find is either Newton's method converges brilliantly or it fails spectacularly. Now, this is an important mathematical question, but because of what I said, just try it and see what happens. It's a pretty manageable engineering problem. Okay, let's do another problem. Here I'm asking you to use Newton's method to determine approximation to the solution to cosine x equal x that lies in this interval, and find an approximation to 6 decimal places. And here I'm going to have you first guess, and I keep bouncing back between 0 and 1, but what we're going to do is we're going to start at 1 and go from there, and we're just taking the midpoint of our initial interval. You know what to do. Let's see how you did. Now, the first thing you have to do is you have to put this in the form f of x equals 0, so you have to rewrite it this way, and you're not going to get any traction unless you do that. So now we can write this is f of x in, and if I take the derivative of what the new f of x is, what we're going to get is, and I shouldn't have called it f of x again, but I did. So the derivative of this is going to be minus sine of x in minus 1. So this is our recursion formula. So what I'm going to do is I'm going to plug in 1, and here's another mistake. That really should say x. Well, I should have started with calling that x0. But anyway, what happens here when I plug in 1, I get this value. Then I'm going to take this value and plug it into the recursion formula again to get my next value. These, of course, are radians that we're plugging in. So then I'm going to take this number and plug it in again to my recursion formula, and I will get this number and this number. Now this agrees to, I guess, the right number of decimal points, and I guess that's actually even more than that. That's even, they agree to, it looks like 1, 2, 3, 4, 5, 6, 9, maybe 10 decimal places. Anyway, they agree significantly. Some final observations then. Newton's method is a fancy improvement to the bisection technique that we discussed previously in these notes during the intermediate value property for continuous functions. When Newton's method converges, it converges significantly more quickly than the bisection approach. The speed of convergence is important to engineers, scientists, and mathematicians. But here's a general truth. The fancier the technology, the more fragile it is. The bisection technique always works for a broad class of functions called continuous functions. Newton's method has more stringent requirements. You have to be differentiable, and it can fail spectacularly. Now, the conditions when something works and doesn't work is an important mathematical question, and for this is addressed in advanced calculus courses. But in those advanced calculus courses, it can be shown that a condition sufficient to produce convergence of Newton's method to 0 of f of x is this ratio being less than 1. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.